All right, we're continuing with exponential growth and decay. And now we're going to look at example 4. So we're going to rewrite exponential functions. So it says determine whether each function represents exponential growth or decay. So if you look at a part, y equals 100 times 0.6 raised to the 2t power. So we can rewrite that as 100 times 0.6 squared to the t power. So remember your properties of exponents. A power of a power property says you multiply exponents when you have a power to power. So we're just kind of working backwards just a little bit. So if we do that, then we can do 0.6 squared, which is 0.36. If you're not sure about that, take your calculator here and do 0.6 squared. Hit enter and you get 0.36. Okay, so 0.6 squared is 0.36, and that's still raised to the t power. So it says, does this represent exponential growth or decay? This number here is less than 1, so that means it is a decay function. Looking at part B, we have f of t equals 1.1 raised to the t minus 3 power. Now, if you think about t minus 3, okay, so that would be properties of exponents as well. So subtraction comes from the division property. So quotient of powers property or division. So your quotient of powers property says you subtract from top to bottom. So we can rewrite this as 1.1 to the t power, and then I'm going to subtract, so I'm going to put 1.1, and my negative 3 moves to the bottom. It becomes a positive exponent. Now, I can still rewrite this a little bit more. So this is a number, 1.1 to the third power is a number, so I'm going to have 1 over 1.3 to the third power, because that's on the bottom, right? And then that's going to be times 1.1t. All right, so we can evaluate this right here. So let's see what it says. So we're going to have 1 divided by 1.1 to the third. And that's going to give us about 0.75. So we're going to say this is about 0.75 times 1.1t. And so what we were trying to do was see if this was growth or decay. So since we wrote this in our standard exponential form, this is ab to the x power, or t power in this case. And so this would be our y-intercept. This would be our growth or decay factor. Since this is greater than 1, this is a growth factor. Example 5, modeling real life. You deposit $100 in an investment account that earns 6% annual interest compounded monthly. You also have a savings account with a constant balance of $200. Write a function m that represents the balance in dollars of the investment account after t years. Write a function b that represents the total balance of the two accounts after t years. Then find and interpret B5. All right, so write a function m that represents the balance of the investment after t years. So here's our formula. This is another version, just a little bit more detailed version of what we've been looking at before, and it represents compound interest. So y equals p, your principal, times 1 plus your rate divided by n, so the number of times the interest is compounded yearly. So like if it was monthly, it'd be 12 times in a year, raised to the n times t power. All right, so we're going to use this formula to write a function for our investment here. So if we have y equals p, so I'm going to use m because it says to use m here. All right, so use m that represents the balance in dollars of the account after t years. So we're going to use m and t as our main two variables. So let's say m of t, if we're writing it in function notation, it would be m of t. That's similar to f of x. All right, and then our initial deposit is $100. So we're going to take and plug in 100. And again, I'm using this formula right here. So I'm going to have 1 plus, and then my rate. My interest rate is 6%. Again, you have to write that as a decimal, so 0.06. All right, and then that's over n. N is the number of times it's compounded per year. So we're doing this monthly. Okay, it says monthly, so monthly means 12 because 12 months in a year. And then it's raised to the n times t. N is 12, so it stays 12. And then t is the number of years. So right now, just leave this as t because we're just trying to write an equation here. All right, then we can simplify this down a little bit. Let's see what is. We're going to do order of operations, so we have to do inside parentheses first. So 0.06 divided by 12. And that's 0.005, and then I'm going to add that to 1. So what I did was just evaluate what's inside my parentheses here. So I'm going to have 100, and then times 0.1005. And that's raised to the 12t power. And again, I can use my power of power property if I want to get rid of that 12. I can evaluate this to the 12th power and then just leave that as t, or I can leave it in this form as well. But let's see, what is this to the 12th power? All right, so that gives me that number here. So let's write it down. So 100, 1.06. And that would be to the t power. All right, so that is my function that I'm working with. And then I need to see if I answered the question. Write a function m that represents the balance in dollars of an investment account after t years. So m of t equals 100 times 1.06 raised to the t power. If you want to leave it in this form, that should be fine as well. But that is answer to number, or part A. And then B part says, write a function B that represents the total balance of the two accounts after t years. All right, so remember the second account says you also have a savings account with a constant balance of 200. If we have a constant balance of 200, that means there's no change. So it would just be, let's see, C of t for a constant balance of 200. So there's no change, there's no slope in it. So that would represent your function of your savings account. All right, now it says write a function B that represents the total balance of the two accounts. All right, so the two accounts would have to be added together. So if I take and add the two functions together, it would be 100 times 1.06 to the t power plus 200. All right, and then it says we want to take that function, okay? We want to take this function and, wait a minute, this says write a function b. All right, so let's call this b of t. Running out of space here. Let's see, try that again. All right, so that's b of t. And now we want to find b of 5. So we're going to find b of 5. So all we have to do is plug 5 in. And evaluate. All right, I'm going to start with 1.06 raised to the 5th power because I'm doing order of operations. My calculator may do it if I plugged it all in, but I'm going to do it myself. So this, and then I got to times it by 100. And then plus the 200. All right, so it says $333.83. All right, let's see if I type the whole thing in, let's see if it gives me the same answer. 100 times 1.06 raised to the 5th power. Well, let's see. Just put my parentheses here. Now raise it to the 5th power and add 200. The calculator usually does very well if you enter everything correctly. So you can see that I got the same answer even though I forced it to do order of operations first. I did the 1.06 to the 5th power times 100 and then added the 200, and then I typed the whole thing in and I got the exact same answer. So there's going to be about $333.82 after 5 years. Example 6. The value of a car is $21,500. It loses 12% of its value every year. Write a function that represents the value y in dollars of the car after t years. Use the graph of the function to estimate the value of the car after 6 years. So we know we can write a function y equals a times 1 minus rate, because it's losing value, to the t power. All right, so y equals A. A is going to be our 21,500. We're going to do 1 minus 12%. All right, so y equals 21,500. 1 minus 0.12 is 0.88, so that shows the decay factor, which makes sense because the value of a car would decrease. And then that would be write a function that represents, okay? So we wrote a function that represents that scenario, so that's it. And then it says use the graph of the function to estimate the value of the car after 6 years. All right, I went ahead and graphed this because we're running out of time here. So show the graph. It's kind of hard to see what that value is, but if you go to your table of values and you come down here where it says 6, that's 9984, so that's getting very close to $10,000. So it says estimate the value of the car. So it would be about $10,000 after 6 years.